Alright, so here we go. Take home number 7. It just keeps getting more and more exciting. We've got our function x over x squared plus 2. We're looking at it on a closed interval. And the first task in A is absolute extrema. Okay, for A, when you're finding absolute extrema, it's you're really looking at the same process over and over and over again. This problem's nice because you're looking at a closed interval. We're soon going to get to some problems where it's an open interval and it's a little different, but still it'll be similar to this. So absolute extrema, you want to test your boundaries, right? That's the -1 and the 4. So I would just start, right? I would, off to the side, I would record, hey, what is f of -1? What is f of 4? So f of -1, -1 is -0.333. Just go to 3 decimals on the AP test. F of 4. F of 4 is, working on my calculator here, 0.222, roughly. Okay, roughly 0.222. So absolute extrema, you always want to record the values of your endpoints. Okay, if this were an open interval, like if it was from open -1 to open 4, instead of f of -1, you would have just done the limit of your function as x approaches -1. You still would have gotten -0.333, but you would have replaced this piece in blue with this piece in blue. Anyhow, it's a closed interval. It makes your life easy. Or easier. You're in calculus, so it's not always easy. So, absolute extrema. You always want to record the values of your function at your endpoints. Okay. Now, if maybe they give you a function and they didn't give you an interval, so what would your endpoints be? Well, you have to look at where your function is defined, and you're probably going to be looking at infinity and negative infinity. Anyhow, so you got your endpoints. Next thing you need is your critical points, right? So you've got your function. You're going to need f prime. Okay, so critical points so critical points, this is our work. F prime of x equals 0 when x equals what? Okay, so I'm just going to grab my calculator. I'm going to say, calculator, solve me a derivative x over x squared plus 2. X over x squared plus 2. Tell me when that equals 0. Plus or minus root 2. Next equals plus or minus root 2. Plus minus root 2. Okay, so we're only working on the interval from -1 to 4. So as far as our interval goes, negative root 2 is outside of that interval. So all we care about is the positive root 2. Now, we've touched on it a little previously when we talk about critical points. But just the fact that your derivative is 0 somewhere doesn't necessarily mean it's a critical point. Your function also has to be defined there. So we have a critical point at x equals root 2 because two things. F prime of x equals 0 there, and f of root 2 exists. Okay, I know it exists, well, because the domain of this function here, we usually start with this. The domain of this function is negative infinity to infinity. Okay, so we've got a critical point at root 2. F prime of x equals undefined where? Well, let's see. I should record f prime of x. So what is f prime of x? If you want to know where your derivative is undefined, you certainly should have an idea of what your derivative is. So f prime of x equals negative x squared minus 2 over x squared plus 2 squared. Okay, so is your derivative ever undefined? Well, I notice f prime of x is a rational function. Alright, I'm just saying there's a fraction there. So just make sure you can't ever divide by 0. So is there anything that you could let x be so that the piece I've highlighted here in green is 0? The answer is no. Okay. So f prime of x does not equal undefined. How do I know that, like, quickly? Well, if you know what x squared plus 2 looks like, well, x squared is just like a parabola, right? So x squared plus 2 is that same parabola shifted up 2 units. So if you take all the y values, like along this curve right here, and you square them, you're going to get positive results. So, you know, if you know what a quadratic looks like, and you know what x squared plus 2 looks like, that allows you to answer that quickly. Okay, critical point. So I know when my derivative is 0, you know, within that interval, -1 to 4, and I also said, hey, f prime of x does not equal undefined. Right, so that's the two spots your critical points can show up. So, well, now what do? Well, the only thing I have to do is I'm going to go back up, and I've recorded f of -1, f of 4. I also need to record what f of root 2 is. F of root 2 equals, okay, so I go back, my table, square root of 2, 0.354. 0.354. Cool, so this is all, you know, when you make your decision here for absolute extrema, you're just looking at these three things, okay? So out of these three pieces in green, what's your highest, what's your lowest? Well, my highest is 0.354. That's my absolute maximum. My lowest is -0.333. That's my absolute minimum. Okay, so for A, we're just going to say absolute max of 0.354 at x equals root 2, absolute min of -0.333 at x equals -1. So absolute extrema, check your endpoints, check your critical points, just compare the y values. Okay, next we go to relative extrema. So it says use the first derivative to justify. So this one's going to take us a little longer, but it's not bad. So relative extrema. So that's just like the high points and the low points. And we've already done a lot of work, so it'll help us. So f of x equals x over x squared plus 2. We're looking at -1 to 4. Okay, this is a closed interval, right? Anytime you're dealing with a closed interval, your endpoints are going to be relative extreme values as well. Like, because relative extreme values say, well, compared to the points around it, it's the highest or it's the lowest. Like, so no matter how you draw your graph, and I guess unless it was a flat line, let's say your graph looked like this. Let's say this is your -1, this is your 4. This is not what your graph looks like. Okay, well this here, relative to the points around it, would be a minimum. This one, relative to the points around it, would be a maximum. So you notice, like, at your left-hand endpoint, your function, okay, -1 is your left-hand endpoint. Just to the right of -1, your function is increasing. Well, if you have a starting place and you increase, you must form a local minimum there, right? If it's a left-hand endpoint. As far as the right-hand endpoint goes, like, so I've got my function, and let's say it stops here. Well, leading into that point, if it was increasing, if it increased up to that point, you have a maximum, a relative maximum. If it decreased coming into that point, you have a relative minimum. So this is a little more involved, just because I'm going to ask you to also pay attention to the fact that this is a closed interval, and on the left-hand boundary you'll have a relative extreme value and the right. But so, okay, this is where we go ahead and we're going to break f up on this interval here and identify our critical points and break this thing into a bunch of different intervals and describe where it's increasing and decreasing. So I already have my f prime. Negative x squared minus 2 over x squared plus 2 squared. So that's your derivative. So you want to use the first derivative to justify relative extreme values. This function has a domain of everything. Okay, this lives at negative infinity to infinity. Negative infinity to infinity. That's where this lives. Okay, it's important to show that, hey, there are no discontinuities in here. So I need to use the first derivative to justify any relative extreme values. So if the first derivative goes to 0, or the first derivative goes undefined, then that opens up the opportunity that my function changed from increasing to decreasing, or decreasing to increasing. Right? So if, like internally on a graph, ignoring endpoints, if your function ever turns around, either direction, you end up forming minimums or maximums. Well, these two right here, that would be a result of f prime of x being 0. This one is a result of f prime of x undefined. But what we're getting at here is the only way for your function to turn from increasing to decreasing or decreasing to increasing is if your derivative goes to 0, or your derivative goes undefined, or the function itself goes undefined. So we've already said this function has a domain of negative infinity to infinity. So no worries about it going undefined. The next would be to say, well, where does f prime of x equal 0? Well, we will only have to look from negative 1 to 4, and we know from previous work f prime of x equals 0 at root 2 when x is between negative 1 and 4. And then we also know f prime of x does not equal undefined when x is between negative 1 and 4. So we only have one critical point. Okay, our critical point is at root 2. It's like your one interval separator. So when we look at the intervals, and what f prime is doing, we have this interval from negative 1 to root 2, and this interval from root 2 to 4. You only have two intervals. Okay? So we're just going to record what is f prime of x doing on those intervals. So I just take a number from this interval here, okay? Zeros in that interval, and I plug it into f prime. And I'm just looking to see, do I get a positive or negative result? So I go to my table, I plug it in. Well, into my table, I guess I need to put the derivative. So I'll copy that, my 89, I'll paste it in here. Okay, so table. So 0, I get a positive result. Okay, so when I plug 0 in, I get a positive. So f prime's positive on that interval here. Okay, and then when I plug, let's see, I need to plug a number from this interval in. So I'm going to go with 3.9. So I'm going to plug that into my calculator. 3.9. I get a negative result. So my function, from negative 1 to root 2 increases, and then from root 2 to 4 it decreases. Now this certainly isn't the shape of the graph, right? But I'm just trying to articulate what's going on here. Okay, this function goes from increasing to decreasing. So that one there, that's going to be a relative maximum. That left-hand endpoint, that's going to be a relative minimum. that right-hand endpoint, that's going to be a relative minimum. Now we see it, we just have to justify it using calculus, okay? So here goes the justifications. This is the part you love the most. You know what's going on, but now you have to put it into words, and so here we go. So local max at left-hand endpoint. Local max at left-hand endpoint when x equals -1, because f prime of x is greater than 0 on -1 to root 2. Oh, and I said local max. Sorry. I meant local min. I already said it's a min. When we looked at the picture, I don't know why I said max. Now we'll go to this right-hand endpoint, okay? Local min at x equals 4. And I'll just put, I'm trying to make sure I cover all my bases. I'll just say which is a right-hand endpoint. Because f prime of x is less than 0 on root 2 to 4. Okay, one more. Local, and it's an absolute, so you can say local / absolute max of it said relative extreme. Okay, so local max of, let's see, what was f of root 2? Going back to our work, f of root 2. Sorry, I'm making you dizzy here. 0.354. Local max of 0.354 at x equals root 2, because f prime of root 2 exists, or sorry, f prime of root 2 equals 0, and f prime of x is greater than 0 on -1 to root 2, and f prime of x is less than 0 on root 2 to 4. Perfect. I never, let's see, I want to go back through this. I'm looking at this bullet right here. Local min at left-hand endpoint. I should say local min of, so when x was -1, what was the y value? When x was -1, -0.333. Local min of -0.333 at left-hand endpoint when x equals -1. Okay, local min of 0.222 at x equals 4. Okay, now we're on to part B. So you've got your relative extreme values, and you've used the first derivative. When we say first derivative test, that's just saying use the first derivative to justify. So 2 says, for this new function, determine any relative extrema using the second derivative test. 4x to the 1/3 minus x to the 4/3. 4x to the 1/3 minus x to the 4/3. I hope that's... Make sure I copied this right. Yep. So that's your function, f of x. So we're looking for relative extreme values using the second derivative test. The domain of this function is -∞ to infinity. I know that because I can raise any number to the 1/3 power. I can raise any number. Well, I think I can You can raise any number to the fourth and then take that anything and raise it to the 1/3. So the domain is negative infinity to infinity, which is nice. Relative extrema are going to occur when your function goes undefined. Sorry, not when your function goes undefined. When your derivative goes undefined, or your derivative goes to 0. So that says you really need to find your critical points as the only places it could go. So critical points work. Well, we need f prime of x. So f prime of x is 4/3 x to the negative 2/3 minus 4. I'm just using the power rule. 4/3 x to the 1/3. I'll recopy this. F prime of x equals 4/3 times x squared to the 1/3 minus 4x to the 1/3 over 3. So I'm just looking at the domain of f prime, like where it's defined, and as it sits right now, I notice that if x were to be 0, you'd get a divide by 0 error, right? So that means f prime of x is undefined when x equals 0. Right? F prime of x equals 0 when x equals, so we'll ask the 89 to solve this. So solve me, I differentiate, 89 solve, differentiate, okay, 4x to the 1/3 minus x to the 4/3. So when is the derivative of that thing 0? When x equals 1. Oh, yeah. When x equals 1. Okay, so here's the thing. The prompt says determine any relative extrema using the second derivative test. We've just talked about critical points, and we've said you might have a relative extreme value here or here. Now, you cannot use the second derivative test to justify a relative extreme value if your derivative is undefined at that spot. Okay, so the second derivative test is only used to justify relative extreme values when your derivative is 0. So we're only going to work right here. I'm trying to determine whether I have a local maximum or a local minimum at x equals 1. That's all I'm trying to do here. Okay, I know something interesting seems to be happening at 0, but I don't care. The prompt only asked for relative extrema using the second derivative test. So I'm only looking at that one because it's the only one the second derivative test applies to. So local max or local min? Well, this is going to go one of two ways. Okay, you're going to plug 1 into f double prime. Okay, so you're going to plug 1 into f double prime. If it's greater than 0, okay, if f double prime of 1 is greater than 0, that means you're concave up, and you would have found a local min. If it's less than 0, it's concave down, and you would have found a local max. So your justification here for a local extreme value, and if it's, sorry, there's a third option, if f double prime of 1 equals 0, it's inconclusive. Alright, so it doesn't say anything about it. Okay, so all we got to do is plug 1 into the second derivative and look at the sign. If it's positive, okay, you've found a local min. If it's negative, you've found a local max. So, on my 89 here, I'm going to ask for the second derivative of 4x to the 1/3, 4x to the 1/3 minus x to the 4/3. So I said 89, please give me the second derivative. Okay. I'm going to copy that second derivative, which is this. Okay, f double prime of x equals negative 4 over 9x to the 2/3 minus 8 over 9x to the 5/3. Okay, I'm going to copy that second derivative into the table. I'm going to plug 1 in, and I'm going to see if I get a positive number or a negative number. So I paste it in there. I go to my table. I plug in 1, and I get a negative number. F double prime of 1 is less than 0. Okay, I found a local max. Local max at x equals negative 1 because f prime of 1 equals 0 and f double prime of 1 is less than 0. Done. Okay, that's all you got to say. So look at how short that is if you can use a second derivative test. It's really short and quick and easy way to justify a relative extreme value. But it's kind of limited because you can't use the second derivative test when your first derivative comes up undefined. So B says any points of inflection justify your results. So 2B. So now we've got kind of those intervals of concavity. Your function was never undefined. Your first derivative we've calculated. Intervals of concavity says that's when inflection points are when concavity changes. So inflection points. So I need f double prime of x again. So f double prime of x, we've already calculated it. It's right here. So if f double prime, if it keeps track of concavity, the only way that f double prime is going to change signs is if f double prime goes to 0, f double prime goes undefined. I mean, we could this is kind of redundant. We'd say, okay, so we're looking for f double prime of x equals 0. These are like our interval separators. F prime of double prime of x equals undefined. Or like f prime of x was undefined. Or f of x was undefined. That's kind of redundant, but you're kind of working backwards, right? So those things, those right there would be your interval separators. Okay, so let's look. Is f double prime of x ever undefined? Yeah, when x equals 0. Because in both of these fractions here, if x is 0, you get to divide by 0. Okay, is f double prime of x ever 0? So you'd ask your 89, or you'd ask Wolfram to do it. F double prime of x equals 0 when x equals 2. Okay, was f prime of x ever undefined? I think it was. F prime of x is undefined when x equals 0. Okay. F prime of x was undefined when x equals 0. And f of x does not equal undefined. So we've got our really our interval separators here, and it looked like let's see, f double prime of x equals 0. I wrote this wrong. F double prime of x equals 0 when x equals negative 2. I don't know why I wrote that. Okay, I just corrected that right there. So your separators really are at negative 2 and 0. We're looking for inflection points. So let's write out our intervals. So you've got negative infinity to negative 2, negative 2 to 0, and you have 0 to infinity. So we're looking for changes in concavity. So I just want to record the sign of f double prime when you plug a number from this interval into f double prime, a number from this interval, and a number from this interval. So if you have f double prime sitting in your y equals, let me make sure and do that. So I've got that. Okay. Wish you could see my calculator. So I'm going to plug like negative 10 into f double prime. I get a negative result. I'm going to plug negative 1 in. I get a positive result. And I'm going to plug 10 in, and I get a negative result. Okay, so a couple possible places where I have inflection points. Okay, I might have one at negative 2 and I might have one at 0 because it looks like concavity changes. So there is our sign chart. So if you're going to have an inflection point, a couple things have happened. Okay. I know you're ready to shut this video off, and I'm ready to go home. It's 9 o'clock on Sunday night, but we're going to finish this out and do this thing the right way. Okay, inflection point. Concavity changes, and you can draw tangent line on F. Now that last part is really, I mean, it's a super fine detail, but like I said, we're going to do this the right way. Sometimes you can draw the tangent line, like if this were your graph, if that were the graph of f, you'd have a vertical tangent right here, okay? A vertical tangent. You can draw that tangent line, but here's the problem. At that point, f prime of x is undefined. So in that picture, when f prime of x is undefined, you have an inflection point. But if the picture would have looked like this, concave up, concave down, here's an instance right here where you can't draw the tangent line because you have a point of non-differentiability. So I think, let's try to remember, I know f of negative 2 is defined. And I know f of 0 is defined. So both the points exist on the graph, but we just have to make sure that we can draw the tangent line there. Now if f prime of x exists, if it exists, then you can definitely draw the tangent line there. If f prime of x is undefined, well then you have to do some searching and say, which of these two cases is it? You know, is it one of those? Because if it's the vertical tangent case, then you would still have an inflection point. So f prime of x exists, that makes us happy, then we could say yes. So did f prime of negative 2 exist? So let's go back to f prime. Okay, f prime was only undefined when x equals 0. So f prime certainly exists when x is negative 2. So we've got an inflection point there. Inflection point at x equals negative 2 because f of negative 2, low battery, and I'll plug this in real quick, f prime of negative 2 exist, and, okay, let me grab my charger. So my computer froze real quick on me there, so I'm just, the last 5 minutes of audio, I'm just about dubbing some new audio in here. So I think it just takes my computer a sec before it unfreezes. So we're up here, we're arguing an inflection point at -2. And we, all we've got to be able to say is you can draw the tangent line at -2, and concavity changes at -2. So as soon as this thing unfreezes, there we go. So the first part was saying you could draw the tangent line. The second part here is you've said, okay, f double prime of x is less than 0, negative infinity to -2. And now we're going to say f double prime of x is greater than 0 on -2 to 0. So there's our inflection point at -2. And then we move to justifying the inflection point at x equals 0, which is a little interesting, right? You look at the table down below. We'll scroll back down to it, and you saw that concavity certainly is changing at x equals 0, but it takes more than concavity changing for something to be an inflection point. You also have to be able to draw the tangent line. Well, the first check that you could do to being able to draw the tangent line is make sure the function is defined and make sure that the derivative is defined there. But just because the derivative maybe is undefined, you could still have an inflection point. Look at the two graphs that you're seeing right there. That vertical tangent one, the slope of that vertical tangent is undefined. So right there the derivative is undefined, but it's still an inflection point. So what I ended up doing for this is if you graph your original function, you'll notice that you do have a vertical tangent at x equals 0, and the graph ends up looking something like the one I'm sketching right there. So yeah, we have a vertical tangent, which is why the derivative is showing up as undefined, but we still have a change in concavity at x equals 0. So it is an inflection point. Now the justification here is a little bit different, and I certainly don't think you'd have to go to this extent on the necessarily on the AP test. I don't see them asking you to justify an inflection point where you have a vertical tangent on an extended response, but could show up somewhere on a multiple choice. So maybe they'd say something like, if f prime of x is undefined, can you still have an inflection point? Well, the answer is yes. So I'm just writing here inflection point at x equals 0 because f of 0 exists, and although f prime of 0 is undefined, there exists a vertical tangent at x equals 0. So that's half the justification. You can draw the tangent line, and the second half of the justification is just showing that concavity in fact changed at 0. So if concavity changed, your second derivative changed signs. So that's the last part of this justification is what you're going to see there. So we're all done with that. I think this last part I'm just finishing that last interval. So job well done. Thanks a lot. That was a difficult problem, but I appreciate you persevering and pushing through it. So good job.